Okay, I gotta go through this kind of fast. Probably have to put two videos together, but let's see here. So this is for the first problem. This is the different gear orientation. So this one's pretty simple. Because the distance traveled by the bigger one, um, there's no slip on the belt, assuming. So the distance traveled by the bigger one is gonna be the exact same as the smaller one. So that means that this one's actually going to have to spin faster to cover the same distance. So you can actually just use the ratio to find how fast it needs to spin. So 400 rotations a minute, 41.9 rads a second for the smaller one, because we're trying to find out how fast that one gets to, 400 rotations a minute with this one's accelerating. So this bigger circle is actually going to be half of that. From there, you can just use basic kinematics to solve for the time, because we know this is constant acceleration. You can do that for each of them, so the ratio is the same for both of these. So for this one to get to 41.9 rads, it's going to be the same for that one. So you can just solve for the time using the same equation. So now this one's actually twice as small. So that means it's going to have to, spin twice as fast. Pretty simple, so you can just solve for the time for those that way. So for 2, this one's the one with the load, trying to lift up the load with the gears. So we have a bigger gear and a smaller gear, and then the cord's being wrapped around, the gear when it's lifted or whatever. So the radius of what's lifting it is 15 inches. The radius of the actual gear is 18 inches, and the smaller one is 3 inches. So basically, I just solved for the distance to raise it, which is 240 inches, and the distance of the 15-inch circumference. And I just solved for the total rotations needed, and then I just converted that rotation to distance based on the 18-inch circle, which gives us a distance there. And then I just divided that distance by the distance of the circumference of the smaller one to get the rotations needed for the smaller one. So pretty simple there. And then I just converted that to radians, the total amount of rotations needed, because we're going to have to bust out some kinematics. I also converted the rotations per minute, 120 rotations per minute to rads a second, divided by 5 seconds it takes to reach that speed, gives us an acceleration in rads a second squared. And then I can just solve for the distance. So this is the total, rotations needed for it to accelerate to 120 rads a second. And that takes 5 seconds. So for the remaining time, we just use the difference in rotations. So we know it takes this many. We've already gone this many, so you can just subtract them and then solve for this based on the 120 rotations a minute. Solve for the remaining time, add them together, and that gives you the total time to raise that guy. So this one's the circle. This one's the circle with the different points, and it gives you velocities in different directions for the different points. So for this one, you just use this equation. So velocity at A is going to equal the velocity at O, because the whole thing's moving in some direction, times or plus the angular velocity crossed with the distance from A to O. So that's -6. The velocity is clockwise, we believe. So the cross product is just going to give us something in the j direction, because we're crossing I and k. It's going to be in the j. And then I just broke this up into components. So VAX is going to equal V naught x, because there's no I component. And then the y component is given to us. It's going to equal the whole thing moving in the y direction plus the angular velocity times 0.6, or plus times 0.6. And I did the same thing for C. Just crossed them, gives us a value in the j direction. Just separated them into x and y's. This one is given to us, the x velocity, so we know this means this has to be the velocity of the whole entire thing. And then from there, you can just plug it into our original equation. So we know VA in the x direction is going to be -1.4. So from there, you can just solve for the angular velocity in this one now that we have the a and the a and the y value, and you can solve for the rads that way. And then you can plug the rads back into this equation to get v naught in the y direction, to get the total amount of movement. And then from there, you can just solve b. So it gives us the negative 7.4 already, so we just need it in the y direction, which we solve for right here. So we know that they're equal in the y direction. Using the vector addition, you can just solve for the magnitude and the angle. So pretty simple. All right, so for this one, this is the one with the slider, and point DE is moving up, or yeah, it gives you it's moving up clockwise. It gives you that in the question, and we're just trying to find the velocity at A and point B. So we're going to use this equation again. So this is velocity of A is the velocity of the whole thing crossed, or the angular velocity of the part that attaches them crossed with the distance. So I just started plugging in numbers. So I just calculated the, since it's going clockwise, it's going to be in the negative k direction. The vector is only in the x direction for DE. And that's going to give us the velocity of D, which is only in the y direction, only in the dj direction. So from there, I just went back to the original equation, and this one, and I just split it into components. So I just split it into components as far as A goes. Yeah, so I just split it into components here. So we know that this one in the y direction is going to equal 0. So that allows us to solve for the angular velocity of A. And then you can actually just plug that in and get the velocity at A at that point. Because velocity at A is only going to be in the x direction because it's bound to the bar. So from there, I just calculated the vector of dB now. And the angular velocity is going to be the same. So you can just use the exact same equation with the angular velocity that you solve for, because the bar is connected. You know, it's one long bar. And you can solve for the velocity for that one as well. Pretty straightforward. Okay, so this is the one with the two balls. Yeah, this is the one with the two gears. So the one with the two gears, basically you're just trying to find the instantaneous center of rotation for AC. So we actually know the instantaneous center of rotation. It's going to be this fixed point, because the instantaneous center of rotation for any fixed rotating axis is going to be the center. So the instantaneous velocity, or the instantaneous center of rotation, is going to be, 0.3 to the left for C, and for A, it's going to be 0.3 to the left for A, 0.3 to the right for C. So that one's pretty straightforward. The angular velocities, you can actually just calculate by where it's connected to the circle, because the angular velocity is going to stay the same. You just got to basically find the distance for each, from how far it is from where it's connected. So calculate that pretty easily. It's just, all right, sorry, I got cut off, so I had to start recording again. So yeah, basically I just separated it into components, solve for WE in terms of, or omega E in terms of omega, the bar AB. Plugged them into each other. You can plug this one back into that equation, solve for that, and then you just have to do the cross product one last time to solve for the velocity at E, that location in the middle. And yeah, that'll give you the rotation of, or how fast that entire circle is moving. So all right, so for this one, this was the bar sliding down. The one part is in like a channel, so it's only moving in the y direction. So because of that, we can just convert the rotational velocity of BC into rads a second. And we know that VB is fixed, so you can actually find the velocity that way, just using the distance and the angular velocity we saw for earlier. And the point at VA is actually going to be the exact same because it's connected. I mean, the bar is not changing size, so it's not going to be accelerating. It's just going to have that velocity that it has, and that's only going to be in the y direction, as mentioned before. So I named it normal and tangential in this one. So from there, you can just solve for the acceleration just using the omega squared r, and you can solve for the angular acceleration that way. And I just separated it into components. Obviously, we don't know what the angular acceleration is of those two parts because it's going to be different than the actual acceleration. And yeah, from there you can just separate them into equations. So we know it's only going to be in the y direction, which I labeled an A as this one, which allows us to solve for the acceleration in the A direction because we only have it in the B direction. And then from there, you can find the acceleration at point D as well by just working backwards and using the new distance that you found. Pretty much using the same equation and just working backwards. So pretty simple for that one. So this one was the circle rotating, and it's like a rope being pulled. So for this one, I just solved for the velocity in terms of feet per second. I did this one all in feet per second. Found the angular velocity in rads a second and the acceleration. So from there, I just found the acceleration at the center because it's actually rotating around A. So I just used the distance between A and the center, which is 3 inches. And you can just find the acceleration that way, just using the rads and the distance. And then from there, you can find the acceleration at AG by just using the rads and the distance again. So pretty simple for that one. And then from there, I just used the acceleration at AB and just converted everything into tangential and normal components. So at point B, we know that, it's pointing that way because of how the rotation works, and that way because of, where exactly it's moving. So yeah, from there you can just plug everything in and get the acceleration in each of the directions at point B, and then you just have to square them and solve for that way. So for point C, same exact thing. It's just the acceleration of, it's just so in this case they're pointing opposite and this one's pointing down because of where point C is located. If you look and where it's rotating. All right, sorry, I keep running out of space. So, I think I almost finished this one. So, yeah, we pretty much just solved for the components for each one in the normal and tangential direction based on how the circle's rotating. So pointing in versus pointing down, and you can just put them into that form, separate them, solve for basically how fast it's moving based on the rotation versus on the acceleration from it being pulled into the center. So you just do that for each point. Pretty simple, and yeah, that's pretty much it for that one. So for I'm gonna do 10 first, I think. So for this one, pretty straightforward. We just use the so we just use this equation, which is the acceleration. So this equals acceleration. This is the acceleration crossed with the distance, or the angular velocity. Sorry, the angular acceleration crossed with the distance. This is also going to give you acceleration. That's angular velocity crossed with the actual velocity. So basically, you just solve for both of those. Pretty simple. So you just cross the angular velocity with the distance from P to A. So that's just the center to the point on the edge P, right there. And you just do the cross product, and it returns basically these vectors. So it's rotating in every single direction in this case, because it's rotating this way, and then also it's rotating, that way. So basically, you just put everything into vector form, and then I think I just added them all up in this case. Yeah, I just added them all up. I divided it by 12 just to convert it to feet. But yeah, that's pretty much it. So you just are using the acceleration because it tells you, it basically gives you the angular velocity already, and the acceleration from there you can just solve for and then plug everything in and get the acceleration. So pretty straightforward for that one. So for 9, this was the bar on the slider, but the slider is in the y and z directions, so we know there's going to be so we can't just, put it into the equation, separate it by I and j, and then solve for the 0 equation. So in this case, I just started writing everything out. I basically just made a triangle of AP, BP, and then the wall, and just found the distances between them. And then from there, I just found the vectors for like the distance BP and AP. So, because I know I'm going to end up using those for the cross product. So let's see, and we're solving for the angular velocity and the angular acceleration of the rod attached at B. Okay, so just the top rod there. So basically, we know the velocity at P is going to equal the angular velocity of this member, right? Because this is rotating. However fast that's rotating, P is attached to that, so it's going to be rotating the exact same speed. Same with the acceleration. However, it's accelerating. So basically, I just use that to solve the velocity at P, and then for the acceleration at P, I just use this equation, which is the tangential and normal velocity or accelerations. We now know the velocity, and we have the r vectors, and we know the acceleration is 2 rads a second clockwise because it gives us that in the equation. So you just cross that with the distance vector and then minus the omega, which we solve for the angular velocity in the other page, crossed with that same distance vector. So that's going to give us the acceleration at P. And then for the velocity at P, it's basically just the same thing. It's just the angular velocity crossed with the distance vector. And that just returns us a vector with the acceleration as the variable, because we don't know what the acceleration is. So, and then I just solve for the velocity, because I just solve for the velocity relative to the actual bar itself, the bar that's moving. So you can find that by using this simple equation. Even though we don't know the angular velocity of BD, you can just do the cross product anyways, just to give you, some points. Because this is going to go in both directions, like we said, because it's at an angle here. So even though it has it in these points, you can actually still separate this, and we know that the velocity at P is going to be the velocity of BP, and then the velocity relative to that. So we know the velocity at p. We're just looking for the relative velocity and the angular velocity. So from there, since we know how fast p is moving, you can just put it into I and j components. So this is how fast it's moving in the I direction. This is how fast it's moving in the j direction, because we solved that with the cross product up there, just crossing the angular velocity with the distance. And yeah, from there you can just solve for one of them. So I just solved for the angular velocity in terms of v relative, plugged it back in to this equation, and that just gives you v relative, and then you can use that, sub it back into this one, and solve for the angular velocity. So that's how I solved it. Thanks.